last week. And after that, we will go to IUPUI, Indiana University, University in Indianapolis for postdoc studies. We'll be working on chemical biology. So with that, I will give to Sarah who will continue about his work with chemistry.
Thank you, Jerome. Do you hear me? So, thank you everyone for coming in. Today, I'll be talking about development of cold catalyzed glycosylation and synthesis of digitoxin phenolphthalein. Let me show you the brief outline that I'm talking about. Basically, I'll be talking about 3 different projects that I have been working on. So, the first topic I'll be talking about will be gold catalyzed synthesis of 2-deoxyglycosides, and second will be gold catalyzed synthesis of other types of oligosaccharide in glycoconjugates, and third one will be synthesis of oxygen in sulfur-linked digitoxin analogs. Let's begin with the first project, gold catalyzed synthesis of 2-deoxyglycosides. 2-deoxyglycosides are very important glycosides, and they form a wide variety of bioactive isoproducts. For example, ivermectin, well-known insecticides, erythromycin, antibiotics, and well-known anti-tumor antibiotics, landomycin. If you look carefully in these different molecules, they possess 2,6 dideoxyglycosides. In this case, and here you have 2-deoxyglycosides. So because of that presence of 2-deoxyglycosides in various molecules, there are several efforts to synthesize 2-deoxyglycosides, and those efforts can be summarized like this. First, you activate the donor molecule with some electrophile, and then now you form the oxocarbenium ion. That oxocarbenium ion will be trapped by the alcohol acceptor. Now we form 2-deoxyglycoside. But the demerits of those previous methods involves most of the methods use stoichiometric amount of promoter to assist the departure of living group. And sometimes like those promoters can be expensive like ciprofloxacin and toxic like mercury chloride. Therefore, synthetic people think of to develop some catalytic glycosylation. For example, Jean Tosti from UC Berkeley, they developed renin catalyzed 2-deoxyglycosylation. Here they use 1 mole portion of renin catalyst to activate this glycol donor. And there is another example developed by Hin Nguyen from University of Iowa. They invoke palladium catalyst to activate this trichloroacetylated donor to form this 2-deoxyglycoside. And there is another example that they synthesize 2-deoxyglycosides where they use gold as a catalyst. This one, this orthohexynyl benzoates, very fancy donor which has carbon-carbon triple bond in their donor leaving group. That carbon-carbon triple bond will be activated by this gold complex, and then they will form oxocarbenium ion, and that will be trapped by this alcohol acceptor. Now they form 2-deoxyglycosides. This gold catalyzed synthesis is good because the synthesis of glycosylation involves the use of several like functional group containing donors, because these sugars they have like different oxygen functionality, and gold is good because gold bond complex possesses little oxophilic character, and then gold bond complex compound have functional group compatibility, and those catalysts are low air and moisture sensitive. And the beauty of this gold catalysis is they activate carbon-carbon triple bond. Doesn't matter how many functional groups you have, this gold will look for the carbon-carbon triple bond. Therefore, we were interested about this gold catalyzed glycosylation. And we looked carefully into this method and found that this method involves first the synthesis of very fancy donor, and then the byproduct they form is isocoumarine, which is pretty big. And then the other difference is like this involves several steps to synthesize this donor. We think of, can we use some simple glycoside to activate this glycoside from the 2-deoxyglycosides? We think of preparing this simple glycoside where X represents heteroatom. It can be oxygen, it can be sulfur. And then because gold selectively activates carbon-carbon triple bond, this carbon-carbon triple bond upon activation, the lone pair of this heteroatom should undergo 5 indo-decyclization in this particular donor, and then that should be able to furnish oxocarbenium ion. And then we looked carefully into the literature and found that similar donor has been already synthesized. And then DRU from Shanghai Institute of Organic Chemistry, they developed these different donors and tested the reaction, found that those donors are not active enough to furnish product. And we think of, is there any way to activate this kind of simple donors? Probably sulfur can be the option for us. The good thing about sulfur is more nucleophilic than oxygen. And in glycosylation, high glycoside donors are more stable than traditional oxygen glycosides. And as I told you before, since we have carbon-carbon triple bond here, this triple bond can be activated by gold. Now you can form oxocarbenium ion and you can form 2-deoxyglycosides. With that idea, we went ahead and synthesized different donor molecules. First, we use this glycol and we convert this glycol into anomeric acetate. And this anomeric acetate was activated by BF3 insert. In one step, this anomeric acetate will furnish the desired donors we want. For example, we synthesize various donors. For example, this glucoside donor, this is C4axial galactoside donor, and this is oligoside donor. Here you have C2-deoxy and this is 6-deoxy, and this is oligoside donor. And these two donors, these were, for example, this one was synthesized from this glucoside donor. First you do the deacetylation followed by benzylation, and then this one was synthesized from galactoside. This donor will serve as a more reactive donor for our galactosylation. After we synthesize these various donors, now we did the optimization of reaction condition. For that, first we tried the silver triplet only, 10% more, and we use this glucoside donor. This reaction, when we heat reaction around 40 degrees centigrade, even for 2 days, we got no product. Now we switch this silver triplet into gold NTF2. This gold NTF2, 2.5%. I observe slight amount of, like trace amount of product on the chill. See, this case, we think of maybe instead of having this triphenol phosphine ligand, we can substitute this triphenol phosphine ligand with somehow electrophilic ligand here. This electrophilic ligand should be more reactive in our chemistry, should be more reactive than the one with triphenol phosphine. When we get that reaction, found that non-smoke interesting. And that is, what is the solution for this? We think of, maybe instead of having this tightly held ligand like this chloride, counterant like this chloride, we can substitute that chloride with triflate. So because like triflate is loosely held, this coat should be more cationic, more electrophilic. So for that purpose, we react this gold chloride with silver triflate 2.5 mole%, and basically we make 2.5 mole% of gold triflate, and that condition we observe 12% conversion of the donor. And finally, we found that the condition with this 2.5 mole% with this more electrophilic ligand containing catalyst with 10 mole% silver triflate, after 22 hours we got almost quantitative yield. But the problem here is the reaction time is quite high, quite long. Therefore, we increase the catalyst loading from 2.5 mole% to 10 mole%, 5 mole%, and this time we have 10 mole% silver triflate. That reaction complete in half an hour to furnish the desired disaccharide of glycogen conjugate. And we also see what happens if we have just 5 mole% gold triflate. That reaction took like 6 hours, and I observed some leftover donors in the reaction. So from now, like we figure out that 5 mole% this gold catalyst in presence of 10 mole% silver triflate is the optimal reaction condition. And with this condition, we just want to make sure does sulfur required in our donor. So for that purpose, we synthesize simple O-glucoside donor and use this optimal reaction condition. Even for 2 days at 40 degrees centigrade, we didn't observe any TART. That means sulfur is playing a role, and this confirms our chemistry. With this control experiment, we went ahead and did scope and limitation of our chemistry and found that our donors, the donors with the acetate paracetylated proteinated donor and perbenzylated proteinated donor. For this case, glucoside donors can react with various acceptor like primary acceptor, like this one, carbohydrate react primary acceptor, and this one is secondary acceptor where you have the cholesterol as acceptor, and then this one secondary acceptor where this also react with glucoside donor. So in various donor, various conditions, various acceptor react with our donor and furnish the desired product almost quantitative. And what if when we have SHPO oxygen axial, basically from galactoside donor? For this donor, we also observe almost like very excellent yield, and then almost alpha only. Most of the cases we got like alpha only here, and this one also we observe alpha only. So this tells us that galactoside also react well for our chemistry. And with that, because of presence of 2,6-dideoxy sugars in various natural products by the molecules, we think of do the scope and limitation for those donors as well. When we did that reaction, found that in all kind of acceptor, primary acceptor, secondary acceptor, and tertiary acceptor like N and O, in all kind of acceptor, our donors give excellent yield. To furnish disaccharide like this one or glycoconjugate like this. So with this, we think of what is the mechanism Is it really 5 deep cyclization? For that purpose, we try to identify the byproduct formed in the reaction mixtures. The problem of this byproduct is highly volatile, very small molecule. Therefore, we synthesize very simple glycoside mimic. That means like we protect our hydro with mum, and this SO-acetyl will furnish as a will mimic the donor. So when I did this reaction in deuterated chloroform using that optimal reaction condition, found that this crude NMR. Basically, these two large peaks resemble with the commercially available dimethoxymethane, and these peaks, this one from the residual solvent, and this is dichloromethane from this compound, and then leftover peaks are from this dihydrotherapine. That means our reaction going like this mechanism. First, you activate this carbon-carbon triple bond with gold, that I need gold, and this will facilitate to undergo 5 deep cyclization to furnish this sulfonium ion, and this sulfonium ion will collapse and furnish this oxocarbenium ion here, and this oxocarbenium ion will be trapped by alcohol acceptor and you form 2-deoxyglycoside. But this gold complex will undergo proto-deoxidation to furnish this byproduct plus catalyst will go into the catalytic cycle. This is the mechanism we observe. So with that, let me summarize my first project. I showed you how I synthesized 2-deoxyglycosides by gold catalysis, and I also showed you the mechanism how this reaction is going on. From here, I will talk about second part of my talk. Gold catalyzed synthesis of other types of glycoside. Glycosides are very important and they involve in several biological processes in living beings. And for example, there are like some very big oligomers, for example like GLB-H, which is breast cancer associated antigen, SIB enveloped glycoprotein GP120, N-linked glycan, and tetraengineering prostate specific membrane antigen. These are like some example of this oligosaccharide containing molecules which has very important biological activity in living systems. Because of that, we think of maybe we can utilize our gold chemistry and synthesize C2 oxygen, or for example like the problem here is like you have C2 oxygen here and in some case you have C2 nitrogen. This kind of synthesizing this molecule can be difficult because of electron withdrawing nature of this nitrogen or oxygen. So we think of maybe we can utilize our gold chemistry when we tried this optimal reaction condition for these rhamnocyte donors where you have C2 oxygen here. This condition gave us disaccharide but only 12%. So we ask the question, what is the solution? We think of maybe we can change the number of carbon-carbon link in between the two reactive termini, for example sulfur and carbon-carbon triple bond, or maybe we can put some gel dimethyl group that might force these two reactive termini near to each other and that might help the reaction. With that question, we did synthesize various rhamnocyte donors, and some of the donors, some of the yield I showed here is unoptimized. We synthesized various rhamnocyte donors and did the reactivity of Ramnosite donors study. In that case, when I have 3 carbons in between this carbon-carbon triple bond and sulfur, this gave us like only 30% conversion. When I put jet dimethyl group at C2 with similar carbon-carbon number, that case I see the slight increase in reactivity, 27%. But that is not good enough to take reaction to completion. And I also did an experiment with this C2 carbon containing this specific donor, and this one and the donor with 1 carbon containing between this triple bond and sulfur was not like good to give a product. So at this point, we think of just to compare the reactivity between the donors with these 2 carbon containing gem dimethyl containing donors and 3 carbon linkage with the C2 gem dimethyl containing donor. And when we did this comparative study, found that the S-butadiene gem dimethyl containing donor is the best we can prepare at that condition. And from now on, we think of just to do the comparative study of the donors with gem dimethyl containing and without gem dimethyl containing for this S-butadiene thioglycoside. For that purpose, we synthesize various donors. For example, here, so basically this one I equals to H means like you don't have any gem dimethyl. When you have methyl, so that will be like gem dimethyl containing thiol. So we prepare glucoside donors and galactoside donors, and these glucoside donors was deacetylated and benzylated. As well as we did the benzylation for that particular donor. For this condition, we have the donors without gem dimethyl and donors with gem dimethyl. Likewise, as I told you before, like we want to synthesize sugars where it contains C2 nitrogen. For that purpose, we synthesize donors with C2 nitrogen containing gem dimethyl or without gem dimethyl. That case also we did deacetylation followed by benzylation. And we also made 2-deoxy-2-azido glucosamine derived donors, for acetylated donors and for benzylated donors. With these various donors, we employ the glucoside for benzylated donor for the optimization of reaction study. For this reaction, first we use our optimal reaction condition for 2-deoxy sugars. That case we observe 40% product. And when we substitute this normal thioglycoside with gem dimethyl containing thioglycoside, found that reactivity increases from 40% to almost 70%. And then this conversion is not synthetically useful. For that purpose, we wanted to increase the catalyst loading from 5 mole% to 10 mole%. When we did the 10 mole% catalyst loading and 20 mole% silver tiplate, that case we got 86% is our product. And we also know that for the activation of carbon-carbon triple bond, not only gold bond but also gold 3 can be used. Therefore, we see the reaction. We try to observe the reaction how this gold 3 triplet works. That is when we did the 10 mole% gold triplet, that is we observed 89% conversion. While when you have like normal thioglycoside, this 10 mole% silver triplet will give you 61% conversion. So, and when we only use like 10 mole% gold trichloride within CMOS product. So from this optimization study, we wanted to do the reaction with gold 3 chloride, gold 3 tiflate, because gold trichloride is cheaper than the gold 1 complex we were using for gold C2-deoxy glycoside synthesis. So with this optimal reaction condition, we did the comparative study for different donors. Donors without gel-dimethyl containing thioglycoside and donors with gel-dimethyl containing thioglycoside donors. For this condition, for all the reactions we did, we observed that when I have donors with gel-dimethyl, give higher yield than the donors without gel-dimethyl. This one for glucoside donors, and this one when you have more electron withdrawing benzoate protecting group there, that case the reaction needs higher temperature around 40 degrees centigrade. But like for other case, we can do the room temperature reaction and found that the donors with gel-dimethyl gives higher yield than the donors without gel-dimethyl. So this proves that gel-dimethyl helps our chemistry. Likewise, we also did with rhamnocide. These two are rhamnocide, and this one C2-deoxy thalidomide protected glucosamine derived donors. Likewise, like C2-deoxy, C2-azido glucosamine derived donors. For all cases, we found that the donors with gel-dimethyl is higher yield. So for this purpose, we wanted to make sure what is the relative reactivity between these two different donors. For the purpose, I mixed 1:1 of these two donors. This one, I don't have any gel-dimethyl there, but this one, I have gel-dimethyl there. So when I mix 1:1 of these two donors with 0.7 equivalent of this simple acceptor, after 1 hour, using our optimal reaction condition, I got 67% of the desired part, while 70% of the donors without gel-dimethyl was left over and 10% was consumed. This tells me that the donors with gel-dimethyl is almost 3 times reactive than the donors without gel-dimethyl. So after that, this time also we wanted to employ the donor mimic, and we synthesized this SO-acetal, and when we did that reaction in deuterated chloroform, we observed that this dihydrothiophene byproduct, which was confirmed by NMR. And then I also did control experiment with normal thioglycoside. In that case, I don't have any triple bond here. When I did this, when I react this rhamnocide with this optimal condition, when I have gold 1, there is no reaction. However, when I use gold 3, I observe some of the disaccharide formation. So this tells me that gold 1 will not react normal thioglycoside. However, gold 3 can undergo some minor side pathway to give the disaccharide. With that result, we propose the mechanism like this. Normally, the principal pathway is you activate the carbon-carbon triple bond with gold 3, and you form the sulfonium ion, and now you form the oxocarbenium ions, and you will form this glycoside. And gold again will enter into the catalytic cycle after protodevolution. However, the site minimum pathway will go like this. First, this gold 3 can activate this sulfur and form sulfonium that can collapse forms oxocarbenium ion, and this gold complex will undergo cyclization to furnish this gold complex, and which upon protodeoration you form the byproduct, and catalyst will go into the catalytic cycle. This is the mechanism going on in this glycosylation. In summary, I showed you the gold catalyzed glycosylation involving dimethyl sp3 thioglycoside donors, and where like the donors with dimethyl is more reactive than donors without dimethyl. Also, I showed you the mechanism how this reaction going. After this project, let me switch gear a little bit and talk about synthesis of digitoxin analogs. So digitoxin is an important cardiotonic drug which is used in congestive heart failure, and this digitoxin is sodium potassium ATPase inhibitor. And some epidemiological study shows that this digitoxin can be used as a potential anti-cancer agent. And also it was found that it can also work as a potential agent for neuroprotection. However, the problem of this digitoxin is narrow therapeutic window. So scientists try to make some analogs of digitoxin so that they can increase the therapeutic window, or maybe they can make highly potent analogs of digitoxin. For example, Langnahan et al. From Seattle University, they synthesized alkoxyamine containing digitoxin analog. And Doherty and co-workers from Northeastern University, they synthesized various digitoxin analogs. For example, they synthesized the natural digitoxin, and they also synthesize monosaccharide and disaccharide. Here they synthesize 2,3,6 trideoxy trideoxy sugars containing analogs. So basically this is hemicetoside analog, and they also synthesize rhamnoside analogs. And they also did a study of changing this carbon number HC6, and they found that the hemicetoside, when you have just this R equals to metal, will be the most potent molecule. And likewise, when they have a rhamnoside where R is metal, was the most potent for them. And likewise, recently, our group published the synthesis of digitoxin molecule where we exploit the renin catalysis for the assembly of this trisaccharide glycol. And after we synthesize this trisaccharide glycol, after some steps, we can synthesize digitoxin. Basically, this project will be discussed by Kedar, I think this Wednesday. So I don't want to I don't want to dig into this project anymore. Anyway, so with that result, we were thinking of maybe we can synthesize different analogs of digitoxins. So for the synthesis of all these digitoxin analogs, we propose to synthesize monodigitoxoside containing digitoxin analog, bis digitoxoside containing digitoxin analog. Likewise, here when you see this molecule here, you have C3 hydroxyl pointing up. This is called oligoside analog, and this is oligoside analog where you have C3 hydroxyl pointing up, C4 hydroxyl pointing up. So what we want to do is we want to synthesize this analog and do the comparative study. For example, this monodigitoxoside will be the control for this analog. And we also want to synthesize this oligosaccharide or oligoside containing disaccharide analog. With these analogs, I did a synthesis of oligoside analog where I start the synthesis with D-glucol. After 8 steps, I can make this TBS protected D-ramol, and this D-ramol can undergo glycosylation with triphenylphosphate SBR to furnish this glycoside, and which upon deprotection gave us the desired monosaccharide. And this monosaccharide was purified by HPLC to get alpha-amylic product. Likewise, for the synthesis of oleoside analog, I use this diacetone D-galactose. After 8 steps, I can make D-fucol, and this D-fucol can undergo glycosylation with this digitoxygenine to furnish this digitoxoside, this oleoside analog of digitoxin, and which upon deprotection I got oleoside monosaccharide analog. This reaction I got alpha only. After this, now I have to synthesize oligoside disaccharide analog. For the synthesis of oligoside disaccharide analog, we want to use our Bohr chemistry. First, we will synthesize this disaccharide thioglycoside donor, and this donor can be activated by Bohr 1. Now we can form disaccharide analog after several steps. This is the future plan we will be doing. And then for the model study, first thing I need to synthesize this disaccharide analog. For that, we want to make sure we can make this donor. For that purpose, we synthesize this thioglycoside, which upon LIDBP reduction followed by the reaction with this disulfide, we got thioglycoside. This upon deprotection, we got desired monosaccharide donors. That means we can use this chemistry to make this disaccharide thioglycoside. Likewise, for the synthesis of disaccharide sugars, we want to use our anomeric O-alkylation method. Actually, this method was developed by Daniel from our lab. So when I did that reaction, I got this disaccharide, which upon TBS protection, I can get this TBS protected disaccharide. And this disaccharide will be reacted with this disulfide, and we will get this disaccharide donor. After deprotection, this is the desired donors we want. And this will undergo Bohr 1 glycosylation to furnish this disaccharide. Now, let me talk about our sulfur-linked analog. So, for the sulfur-linked digitoxin analog, we want to synthesize this sulfur-linked digitoxin molecule where you have 3 sugars, and we also want to synthesize monodigitoxoside and bis digitoxoside. The reason we are interested in thioglycosides are those thioglycosides are more stable towards acid, and thioglycosides will be more stable towards glycosyl hydrolase than parent glycosides. And most of the system, thioglycosides are tolerated. That's why we are interested in these sulfur-linked analogs. And the idea is because thioglycoside is more stable than traditional O-glycoside, maybe they might remain longer in biological system and they might show different activity. With that idea, we looked into the literature and found that similar effort has been done by different scientists. For example, Bovini and co-workers, they use this digitoxygenine and convert that digitoxygenine into alkylaminothiols containing analog, and found that this digitoxygenine analog showed binding affinity with MCF cell lines, and then they found that the activity is a little bit higher than the deoxygenin. Likewise, Jensen and co-worker also synthesized this digitoxin limit, where they have this ethylene glycol connected with digitoxygenin with the sulfur bridge. With that idea, we propose our retrosynthesis like this. First, this sulfur-linked digitoxin will be synthesized by coupling this trisaccharide glycol with mercaptodigitoxygenin using our rhenium catalysis, and this trisaccharide can be accessed after several steps from this monosaccharide glycol and this CPO-mercapto containing acceptor. Now the idea is, I want to see if that rhenium catalysis or coupling of this glycol with this mercaptodigitoxygenin works. For that purpose, first thing is I need to synthesize mercaptodigitoxygenin. This mercaptodigitoxygenin was synthesized from commercially available digitoxin. First, you do the cleavage of these sugars, followed by Jones oxidation. You got digitoxygenone, which upon reduction you form equatorial alcohol, and which was methylated, followed by SN2. I got this mercaptodigitoxygenin precursor, which upon deep protection I got mercaptodigitoxygenin. Once I have this mercaptodigitoxygenin, I employ this 6-deoxyalol in our 10% rhenium catalyst. In total, I got 71% beta-only this S-link analog of digitoxin, which upon deep protection I was able to make this monosaccharide analog. That means our rhenium catalysis approach is working. So now the problem is we need to synthesize trisaccharide glycol. For the synthesis of that trisaccharide glycol, first thing I need to synthesize was this CPO-mercapto containing acceptor. For the synthesis of this CPO-mercapto containing acceptor, I employ this galactose pentaacetate. After 5 steps, I can make 6-tosylate containing pseudoglycol. This upon reduction, I can get this pseudoglycol, and this upon methylation followed by SN2, I can get C6-thiacetate containing pseudoglycol. And at this point, the problem is we need to install C3-hydroxyl down. The idea for that one is Evans-Misnu rearrangement. That means first thing you oxidize this thioglycoside, make sulfoxide, and then that can undergo rearrangement, furnish the C3-hydroxyl pointing down. When we tried that reaction with this thioacetate, we got dimer. So that means this thioacetate react with MCPBA and you form dimer of this thiol. So because of that, now I have to change the strategy little bit. First thing, I will deprotect this thioacetate and put DNP protecting group. That because of that DNP protecting group, that MCPBA will be selectively reacting with this thioglycoside. So I got this DNP protected thiol, and then I did MCPBA followed by diethylamine. We shared the correct stereochemistry at C3. C3-hydroxyl pointing down. After this, I did the TBS protection and then did the thioglycosylation using rhenium catalyst. That case, I got beta-only thioglycoside. and this DNP protecting group was cleaned using potassium carbonate in presence of ethanol in methanol. Likewise, I also synthesized C3 mom protected acceptor. For that purpose, first I used this C3 hydroxyl, did the mom protection, and I did glycosylation with paramethoxyphenol, and then upon deprotection I got the desired acceptor. So now I have a desired acceptor in hand and did the key glycosylation study when I have C3 TBS protecting group. That case, our rhenium catalyst approach gave us only 40%. Good thing about this chemistry is I got beta only. But the problem here is the sterics generated because of this TBS. So now we want to change the protecting group from TBS to some smaller group. For that, we use the C3 mom protected acceptor. That case, initially we were suspicious about the selectivity. Fortunately, we got beta only 67% disaccharide. This is how I synthesize digitoxin hydrolyside. So digitoxin digitoxoside, and then with that, next step is the deprotection of this mom in presence of this PNP glycoside. But I was not successful enough to convert this reaction sequence. Therefore, I was not able to synthesize this glycol. Now, what is the solution for this? The solution, the solution can be bomb protection at C3. When I have bomb protecting group there, this is somehow like mom, so should be reactive enough to furnish this disaccharide, and that can undergo can oxidation selectively at this position, and then when you do the elimination you can get glycol, and this glycol upon several steps will give us the desired disaccharide glycol, and that can be used as a donor for the synthesis of digitoxin analog. With that, in summary, I showed you the complex synthesis of 3 different digitoxin analogs, and I also showed you how I was able to synthesize digitoxin disaccharide, and the synthesis of oxygen and sulfur-linked digitoxin disaccharide analog is underway. With that, I want to thank my thesis advisor Jang Ju for his guidance, support, and encouragement in the lab. And I also want to thank my committee members, Professor Suchet and Dragan Axelvik and Professor Tilakaratne, and my committee, my lab members Kedar and Daniel. I have a collaborative paper with Kedar and Daniel, and then Hem Khatri, who is my neighbor in the lab. So, and then Padam and Dr. Lee. I also have collaboration with Dr. Lee, and Raghavi and Katie is here in front of me. So they were the high school students who worked with me. They were very instrumental. And then I also want to thank Dr. Kim for his support and teaching in the mass and NMR. And I also want to thank Department of Chemistry and Biochemistry, University of Toledo, and family and friends, especially my wife who helped me